DeepSeek AI just dropped a paper on the 21st of October 2025 that fundamentally breaks the rules of how we process information in large language models. It is titled DeepSeek-OCR, Context's Optical Compression. We all know the enemy here. It's the context window tax. When you are building a RAG pipeline or an agent that reads massive documentation, you hit a hard bottleneck. Text is surprisingly expensive. A single page of dense technical documentation can eat up 500 to 1000 tokens. If you feed a 100-page contract into GPT-4 or Cloud, you are burning cache and hitting latency walls because of quadratic scaling. We want our models to read entire libraries, but we are forced to truncate, summarize, or chunk data until it loses meaning. DeepSeek just proved that we have been doing it wrong. In fact, their findings suggest a radical future where we might stop using text tokens for long contexts entirely and switch exclusively to vision. As developers, when we deal with documents today, we typically use one of two old ways. The first is the standard OCR pipeline, where we use tools like Tesseract or AWS Textract to rip the text out of the image, turn it into a massive string, and feed that string to the LLM. The problem is you lose the layout, the charts, and the spatial reasoning. The second way is the VLM approach, where you feed the image directly to a model like Qwen 2VL. This preserves layout, but it is computationally disastrous because most modern VLMs chop a high-resolution page into smaller squares, exploding a single page into 4,000 plus vision tokens. That is slower and more expensive than just reading the text. So, you are usually stuck. Lose the context OCR or explode your compute VLM. But this paper introduces a concept called context optical compression, and the insight is massive. The authors realized that text strings are actually an inefficient way to store information. They asked a counterintuitive question. Can we compress text by keeping it as an image? The answer is yes. They discovered that you can represent 1000 text tokens using only 64 to 100 vision tokens and still retain 96% decoding accuracy. This implies that the future of long context AI isn't about extending the text window, it's about rendering your data, even your chat history or code, into an image and letting the model see it. An image of text is mathematically more compressible than the text itself. They achieved this by building a new architecture called the DeepEncoder, but you don't need a PhD to understand how it works. Think of it like a highly intelligent zip file for your eyes. Normally, an image is a massive grid of millions of pixels. DeepSeek's engine works like a smart filter with two steps. First, it scans the image specifically for the sharp, high contrast edges, the curves of letters and numbers, ensuring it can read the data. Then, it aggressively crushes everything else, like whitespace and margins, shrinking the data by 16 times. It takes a huge, high-definition page and squeezes it into a tiny, dense digital packet. You feed the model the full page, but inside the brain of the AI, it only takes up the space of a short tweet. They aren't converting the image to text to save space. They are proving that the visual packet is the superior compression algorithm. But compression is only half the story. The other massive breakthrough here solves the OCR problem I mentioned earlier, where we usually lose the charts and diagrams. The paper calls this deep parsing, because the model is processing the visual structure instead of just hunting for letters. It can translate complex visual elements into code. It can look at a bar chart or a scatter plot and output a clean HTML table containing that data. It can look at a complex chemical diagram and translate it into a smile string. It isn't just reading text, it is converting visual logic into structured code, something standard OCR has never been able to do. The results confirm this theory. DeepSeek tested this on the OmniDoc benchmark against MinerU 2.0, a standard open source solution. MinerU required nearly 7,000 vision tokens to parse a complex page. DeepSeek-OCR achieved state-of-the-art performance using fewer than 800 tokens. In their tiny mode, they used just 64 vision tokens to represent a page, achieving a 20x compression ratio compared to raw text. In production terms, this allows them to generate training data at a scale of 200,000 plus pages per day on a single A100 GPU. So, why does this matter for us builders? This isn't just theory. You can implement this architecture to optimize your pipelines today. Here is the concrete blueprint. First, go to the DeepSeek-I DeepSeek-OCR repository on GitHub. The model weights are public. Instead of using a standard OCR tool like Tesseract, you should swap your ingestion pipeline to use their inference code, especially if you deal with scientific papers or financial reports with lots of charts. Second, you need to implement the Gundam Mode logic yourself using Python. Do not blindly feed every PDF page at full resolution. Use a library like PyMoPDF, import fits, to render your PDF pages as images. Before sending them to the model, check the complexity. If it is a standard text page, use Pillow to resize that image to 512 pixels. The paper proves this specific resolution is the magic number, where text is readable but token usage drops by 90%. You only need to switch to high-resolution tiling if your script detects complex tables or charts. Finally, if you are building a chat application with long history, stop storing the conversation as a JSON string of text. Start experimenting with rendering the old chat logs into a single image canvas. By passing that history image to a VLM instead of the raw text, you bypass the context limit significantly, allowing for agents that can see conversations from weeks ago without blowing up your API costs. If you found this breakdown useful, please hit the like button and subscribe to the channel. I'm going to be doing deep dives into more architectures that are changing the way we build software. Thanks so much for watching, and I'll see you in the next video.